Hi, my name is San, and I'm currently a student in the Math 1D class with Professor Fatemeh Yarahmadi. And today I'm going to present a fascinating and well-known mathematical object, which is the Mobius Strip. The Mobius Strip is a remarkable surface. It is famous for having only one side and one edge, even though that is made of a rectangular strip, which would make it a good example in the study of topology. In this representations, I walk you through the constructions of the Mobius strips and examine the structures of the manifold, explore its mathematical properties, and demonstrate how to calculate both the tangent plane as a given point and a scalar surface integral over a strip. So let's get started. In this sections, I show you how to make a Mobius strip. So first of all, here's a strip of papers of length L and half width W. So first of all, you hold the strip by its ends. Then you give one end a half twist of a 180 degree. Then you tape those ends together to form a loop. So there we go. Here's our Mobius strip. So here is an interesting properties of the Mobius strips is that the Mobius strips is a non-orientable surface and that it had only one side. So if we take the Mobius strip and a pen and we start moving in one direction along the surface of the Mobius strips, we will eventually reach the points where we started at, but on the side of papers. And by the other side, I mean the other side of the rectangular paper strips, because the Mobius strips only have one side. And if we keep going, we will be able to draw the two surfaces of the rectangular paper strips. And this proves that the Mobius strips had only one side, which means that it had no inside or outside. It had only one side and it would be the same no matter how we flip it. And similarly, so it had only one edge. If we trace around the boundaries of the strip going in one direction, we will be able to draw the two sides, two edges of the rectangular paper strips by going in one direction without leaving the pen. So yeah, this also proves that the Mobius strip have only one edge. And the third point is that it is not possible to assign a global normal vector for the surface, because at one point we will have two vectors opposing one another. Like take this part for example, we will have the normal vector pointing up, and at the same time, if we go like half the surface, we will be able to draw another vector, also normal vector at that same point, but pointing downward instead. So in these sections, we'll talk about the manifold structures of the Mobius strip. So what is a manifold? A manifold is a space that locally look like in Euclidean space, even if it's the global shape is complicated or curved in a way. So we take the Mobius strip for example. So we made it out of the rectangular paper strip in 2D space, and if we look closely at it in 3Ds and we zoom in on it like indefinitely, it will look like it is a flat surface. So formally, a manifold could be described using three components. Here's the M is the topological space of the Mobius strip, and S is the Mobius strip itself. Jm is the topological structures on M, and 8 is the atlas, consisting of the collection of charts which, if union, cover the whole space of the Mobius strips. So let's take a look at the topological space M of the Mobius strip. In order to describe the Mobius strip in 2D properly, we need a concept called the quotient topological space. So the quotient topological space is a space that one point or one sections can teleport to the another part of the space. Or in the case of our Mobius strips, it's like gluing or connecting the parts of the space together. And here we define M with one dimension going from 0 to L, and the other directions go from W minus W's to W, and the slash and escape characters means that we apply the relations to both ends of the space, where one point of this end is the same as the other point on the opposite ends. And here's some property of this space. So first of all is a locally Euclidean that I have explained it on the previous slide. The second property is that it's of the Hausdorff space, which means any two distinct points can be space can be separated by the disjoint neighborhoods, which informally means that we can actually tear this apart cleanly. And third point is that it is second countables, which means that M can be built from the countable sets. And as for our Mobius strip, it is two sets, which I will get to it on the next slide. It can be more, but two will do the job. So here are the charts of the Mobius strips. So I divided it at the left chart U1 and right chart U2. So for U1, I defined it to goes at length 0 to 3 pi over 2, and for the right chart is goes from pi over 2 to 2 pi. So if you notice, there is a middle part, which is the overlaps between the two sections, and the both charts U1 and U2 union would be the topological space M itself. Now here comes the interesting part. We have defined the two coordinate charts U1 and U2, which are the open set that together they cover the whole Mobius strips. Each chart is associated with the coordinate map Phi1 and Phi2 that transform the point from the manifold space into the 2D space, and the inverse map Phi1 would take the point from the 2D space onto the whole manifold space. So what the functions allow us to do is to connect the two charts through a transition functions on the overlap regions. So for example, this point on the map is also the same at this point on the map. And yeah, this means that the points in the shaded regions of each chart is correspond to the same areas on the second chart. They just presented in a different local coordinated systems. With the what the function means is to identify the space of U1 and then glue it or identify it together with the space of U2, which means that the two created regions are pointed to the same areas on the manifold space. So here's the parametrize functions of the Mobius strips. So this is the simplified version from what I'm going to show you in decimals. They are of the same shape, but this one goes from 0 to 2 pi, and the other one that I'm going to show you is from 0 to 4 pi. So let's go to test mode. So here is our representations of the torus. So by reducing the torus two parameters like u and v into a single parameter v, we effectively created a lines that loop through it, and then by introducing the phase shift of pi, we then effectively split that loop in half. So let me try to write 2 pi, and here is from pi also to 2 pi. So yeah, here we split that loop into 2 lines, the red lines and the blue lines. So the fascinating part is that we can actually connect these 2 lines using a mathematical technique called convex combinations. The result of it form a surface, and that surface is our Mobius strips. Let me try to hide the torus. So yeah, here is our Mobius strip making from connecting the 2 lines together. So one of the tedious part of this process was to compute the partial derivatives using the product rule, and it took me quite a bit of time to carefully look through the calculation and double checks for errors. But here are the results. The partial derivative of dp over du and the dp over dv. So the original problem didn't specify a particular point for the tangent plane, and since the Mobius strip is a non-orientable surface, we cannot define a global normal vectors. So I chose to compute the tangent plane at the point u equal to 0 and v equal to 0, and by substituting u and v into the derivatives that I calculated, I found the derivative of u with the points that I specified, that is u equal to 0, v equal to 0, and the derivative of that with respect to u is 0, r, and 0, and the derivative with respect to v is r, 0, and 0. Taking the cross products of these 2 vectors give us the normal vector at that point. However, we need to keep in mind that this results only hold locally, because the Mobius strip is non-orientability. It is possible to traverse the surface and arrive at the exact same point and get another normal vectors that is in the opposite directions of ours. Still, regardless of the orientations, they both define the same tangent plane at that point, which in turn out to be z equal to 0, and I show it to you on Desmos. So here is our normal vectors that I calculated from the parametric functions of the Mobius strips, and here the plane in purples is our tangent plane at the point 0, or at this point. Because the Mobius strip is non-orientable, we cannot perform the surface integral over a vector field to calculate the total flow on the entire strip. This is due to the fact that the surface had no inside and or outside. Traversing these strips can reverse the directions of the normal vectors, and as a result, the integral could yield to different opposite values. So instead, I define a scalar field of f of u v equal to v, where the values at each point depend on the width positions that we are at. So to visualize this, I created a heat map using Matplotlib and Matplotlib 2D in Python. And as you can see in the visualizations, the lower end of the strip corresponds to a lower value, and the upper strip, like ends, shows the higher values. That is clearly demonstrated by the brighter colors of the gradient of the heat map. Even though the Mobius Strip is non-orientable, we can still compute the scalar surface integral. So this is because the integral only depends on the magnitude of the normal vectors and not its directions. So the lack of the consistent orientation doesn't prevent the calculation. So to do this, I computed the magnitude of the cross product of the partial derivative. However, the result turned out to be quite complex. So I hide them into the variables a, b, and c as in the slide. However, we don't really need to evaluate the full expressions, and here's why. So the partial derivative dp of the u contain one variable v of degree 1 in all of its dimensions, which means that the cross product and therefore its magnitude also depends on v of degree 1. And if we and we can get v's out of the vectors, and thus the magnitude of a normal vector ended up being an even functions in terms of v, while the scalar field is scalar field v is an odd functions. The products of an odd and even functions is resulted in an odd functions, which makes the entire integrand an odd function by v. So since we are integrating over a symmetric interval and from -1 to 1, the surface interval is 0 due to this anti-symmetry. Since the Stoke theorem requires the surface to be orientable, we can't directly apply it into the Mobius strip. And in fact, any attempt to compute a surface integral this way would lead to inconsistent result, because the lack of well-defined normal vector. However, there's a few workarounds. So one option is to apply the Stoke theorem locally, just as we did earlier with the tangential plane, and by breaking the surface into the small parts, we can use the theorem in a limited way. Another approach is to double the double covering trick. This method is a bit more advanced, and I'm still wrapping my head around it. But the basic idea is to wrap around a Mobius strip twice and effectively turning it into an orientable surface, and then we divide the result by 2, and that way Stoke theorems become applicable in this case. So this is the end of my presentations, and here are some references I found helpful in understanding the properties of Mobius strips. The book is also helpful, but is way too advanced for me to understand, so I decided to watch some videos instead. Alright, thank you for watching. I hope that the topic that I presented is interesting to you, and thank you so much.